In this tutorial, we will be discussing predicting precipitations. Precipitation will occur when the concentrations of the ions exceed the solubility of the ionic compound. You can predict if precipitation will occur by comparing the reaction quotient to the Ksp. Q is determined by the current or given solution concentrations and is compared to the Ksp. You may remember this from when we did equilibrium. Q versus Ksp. If they're equal to each other, you're not going to have precipitation. If Q is smaller than Ksp, once again, you will not have a precipitation because this is unsaturated. And if Q is greater than Ksp, you will have a precipitation because it's above the saturation point. Some solutions, even though the Q is greater than Ksp, will not precipitate unless it's disturbed. These are called supersaturated solutions. So let's do an example of this. So will a precipitate form when we mix PbNO3 with NaBr if the concentrations are after mixing are 0.0150 and 0.0350 respectively? So first thing you need to do is figure out the chemical equation. We have PbNO3 reacting with NaBr. This is going to be a double replacement reaction. Pb will be with Br now, and Na will be with NO3. However, you may remember from previous lessons that not everything is going to form a product. For instance, these are both aqueous at the beginning. The NaNO3 is aqueous, so those are our spectator ions. We want to write a net ionic equation for the solid of PbBr2. So lead 2 plus is reacting with 2Br minus to produce PbBr2. Alright, from here we need to write the reaction quotient. That's going to be the concentration of Pb multiplied by the concentration of Br minus. Because of this 2, I'm going to square it. So we know that the Pb is 0.015. And we know that the concentration of bromine is 0.350. 0.0350. And then we square that. So Q is then equal to 1.84 times 10 to the negative 5. We're now going to compare that to our Ksp. This is to the negative 5, Ksp is to the negative 6. So that means it's greater than the Ksp. So that means a precipitate will form. Let's try another one. Well, a precipitate form when we make CaNO3 with sodium hydroxide. Both of those are aqueous. We have to figure out what our spectator's ions are and what our net ionic equation is. So this is once again a double replacement. So we have sodium coming together with NO3. That's going to be aqueous because of the solubility rules. CaOH2 is the solid we're trying to form. So let's write a net ionic equation. Ca2 plus aqueous plus OH minus aqueous. Because it's a plus 2, that means I need 2 of those. CaOH2. Alright, so from here I need to figure out what the reaction quotient is. So that means that we have both of 0.0175. Q is equal to Ca2 plus OH minus, because of that 2 is going to be squared. So that means 0.0175, 0.0175 squared is all going to equal 5.36 times 10 to the negative 6. This one's a little closer, but notice that even though it's times 10 to the negative 6, 5.36 is still bigger than 4.68. Therefore, a precipitate is going to form. A solution containing several different cations can often be separated by the addition of a reagent that will form an insoluble salt in one of the ions, but not the other. So in other words, you're deliberately reacting another chemical with it to make one drop out and have the other ion still in solution. A successful reagent can precipitate with more than one of the cations as long as their Ksp values are significantly different. Alright, so let's take a look at this question. A solution contains 0.02 molar of silver and 0.02 molar of lead. We're going to react it with as much chromate as we need. If it's red, it's going to produce silver chromate. Lead chromate is yellow. So which will form? Alright, so they give us the Ksps of both of those compounds. What we're going to do is we're going to figure out how much chromate are required for each of those scenarios and figure out which one takes less. Alright, so let's do lead first. Lead chromate, we need, the Ksp is 1.8 times 10 to the negative 14 is equal to the concentration of lead times the concentration of Cr042 minus. According to our question, we have 0.02 molar of the lead. Therefore, we are going to need 9 times 10 to the negative 13 molar of the chromate to form with the lead. We're going to do the exact same process for the silver. The silver ion. Now notice that there's a 2 here, so that means it's got to be squared. Alright, so 9.0 times 10 to the negative 12 is equal to, once again it's 0.02. Then x is then equal to 2.25 times 10 to the negative 8. So let's compare these two chromate values. With lead, we have 9 times 10 to the negative 13. With silver, we have 2.25 times 10 to the negative 8. You're going to need far more of the silver of the chromate for the silver compound to make. So the lead is going to drop out of solution first for that reason. Alright, so let's talk about complex ion formation. Transition metals tend to be good Lewis acids, and when in solution, they form complex ions. Remember, Lewis acids accept extra electrons. Ions formed by combining a cation with several anions or neutral molecules are called complex ions. So notice silver reacted with water. Metals often bond to one or more molecules, such as water, to form a hydrated ion. Water is a Lewis base donating electron pairs to form coordinate covalent bonds. The ions or neutral small molecules attached to the metal ions are called ligands. If a ligand is added to a solution that forms a stronger bond than the current ligand, it will replace the current ligand. So for instance here, silver is with water. Ammonia comes around and it attaches to it because evidently it's a stronger bond there. Generally, water is not included since the complex ion is always present in the aqueous solution. So therefore, they've left the water out of the final reaction. The reaction between the ion and the ligand to form a complex ion is called the complex ion formation reaction. The equilibrium constant for this formation reaction is called the formation constant, Kf. And you'll notice that it's done the exact same way as the ones we've done previously. The products over the reactants. Products over the reactants. And that's how you predict precipitation.